This lesson is going to be on types of chemical reactions. There's many different ways to classify reactions. We're going to classify them as these five: combination, decomposition, single replacement, double replacement, and combustion reactions. Combination reactions are characterized by a single product. You can have an element combined with an element to form a single compound, a compound and element to form a single compound, two compounds joined together, but they always form one single product. Decomposition reactions, in essence, are the opposite of combination. You start with a single reactant that breaks down into more than one product. Again, it could be a compound breaking down to two compounds, or compound into two elements, or any combination of those. Single replacement, a more reactive element can replace a less reactive element in a compound. In a double replacement reaction, two compounds react together to form two different compounds. And then combustion reactions, we will describe those later. So combination reactions, these are usually exothermic. You have unstable compounds or higher energy compounds combining together to form a lower energy compound, giving off energy. And again, it could be an element and an element, such as zinc and sulfur, forming zinc sulfide, a compound. You can have the element magnesium joining with the element oxygen to form the compound magnesium oxide. You can also have two compounds joining to form a larger compound, such as magnesium oxide and carbon dioxide, forming magnesium carbonate. Decomposition reactions, again, in a word, are opposite of the combination reactions. Here you've got a single reactant breaking down into more than one product. So magnesium carbonate, when heated, will form the compound magnesium oxide and the compound carbon dioxide. The compound zinc sulfide, if undergoing electrolysis, can be separated into its component elements, zinc and sulfur. And the magnesium oxide, again, if undergoing electrolysis, can be broken down into magnesium and oxygen. And again, in a word, these are opposite of the combination reactions. So here we have single products, and they are exothermic reactions. Here we have single reactants, and they are endothermic reactions requiring energy to occur. Single replacement reactions, again, always take the form of a compound and an element, such as AB plus C, so compound plus element, producing a different compound and a different element. In the top example, C is replacing B. In the bottom example, X is replacing A. The difference here is primarily that of a single replacement by a nonmetal and a single replacement by a metal. If you think of ionic compounds such as aluminum chloride or magnesium oxide or sodium iodide, the metal is always written first and the nonmetal is always written second. And so if C is replacing the second element here, that is a non-metallic single replacement reaction. If X is replacing A, the first element in the compound, that is a metallic single replacement reaction. So nonmetals can replace nonmetals, or metals can replace metals. We're not going to do any that are going to stray from that. Plus, the element doing the replacing must always be more active than the element that is being replaced. So we have to answer the question, how can you tell if an element is more reactive than another element? For the nonmetals, we're going to stick with the halogens, and that's fluorine, chlorine, bromine, and iodine. Note again, diatomic. In order of decreasing activity, fluorine is the most reactive, iodine is the least reactive, and the more reactive can replace the less reactive and not vice versa. So fluorine can replace chlorine, bromine, and iodine. Chlorine can replace bromine and iodine, but not fluorine. Bromine can replace iodine, but not chlorine, or fluorine. So the one that is higher up, if we look at the periodic table, can always replace the one that is lower down, but the one that is lower down cannot replace anything above it. So iodine cannot replace bromine, chlorine, or fluorine, and so on. So if you look at a particular reaction such as sodium chloride and fluorine, first thing we got to understand is fluorine is going to try to replace chlorine, not sodium. Again, nonmetals can replace nonmetals, not metals. And next thing is the fluorine more reactive than the chlorine? The answer is yes. Fluorine is higher than the chlorine, so it can replace it. And so they're going to switch places, and now we're going to have sodium fluoride and chlorine. Again, note chlorine is a diatomic element. In the second example here, can the bromine replace the chlorine? The answer is no. Bromine is lower than the chlorine, and so that is going to be no reaction. The more reactive element, the chlorine, is already in the compound, and therefore it cannot be replaced by a less reactive element, the bromine. In metallic replacements, again, we need to have an activity series. So we see an activity series here. Lithium is at the top, silver is at the bottom. Lithium is the most reactive, silver is the least reactive. Any element on that list can replace something below it, but not something above it. Note hydrogen is located in two positions. The hydrogen of water is there. The hydrogen of acids is here, and so we need to distinguish between hydrogen of water and hydrogen of acids. So if we look at zinc and lead 2 chloride, zinc is the element, lead is the metal that is in the compound. Again, metals can replace metals, not nonmetals. So we need to find zinc and lead on the activity series. Is zinc higher? Can it replace the lead? The answer is yes. Since zinc is higher up, it will replace the lead, and the two then will switch places, and we'll again end up with zinc chloride and lead metal. In the second example, the two metals involved are calcium and zinc. Finding them on the activity series, calcium is higher than zinc, so zinc as the element by itself cannot replace the calcium since calcium is higher up, so that would be a no reaction. Again, the more reactive elements already in the compound, it cannot be replaced by a less reactive element, so that would be a no reaction. For double replacement reactions, these must form a precipitate, gas, or molecular compound. I'll explain that in a minute. So generalized equation, one compound plus another compound forms two different compounds. Really, we're just going to switch the X and the A. The metal's going to be replacing each other. And so if I start with sodium iodide, lead 2 nitrate, on the product side, we're going to switch the sodium and the lead. So we'll end up with lead 2 iodide and sodium nitrate. So lead 2 iodide is going to be an insoluble compound, a precipitate, and sodium nitrate will remain aqueous dissolved. The idea here about it must forming a precipitate, gas, or molecular compound goes back to the idea of ionic equations. If I have a soluble substance, it's going to exist as ions in solution. If I combine that with another soluble substance that is just ions in solution, and there's no new combination that forms a gas, precipitate, or molecular compound, all I've done is taking one mixture of ions, adding it to another mixture of ions to form a larger mixture of ions. There's no new substance present. I'm just physically combining them. There's no new chemical combination. But if I mix one aqueous solution with another aqueous solution, and one of the ions from each combination or each compound join to form a precipitate, now they're no longer the same. Now we've got a new substance that is formed, and that then is a chemical reaction. And so if we look at these double replacement reactions, again, they must form a gas, precipitate, or molecular compound. In example A, we have a precipitate formed, so that is a true double replacement reaction. In the second one, we have a molecular compound formed, so that is a true double replacement reaction. The hydrogen ion from hydrochloric acid and the hydroxide ion from sodium hydroxide form the molecular compound, something that does not dissociate, and so it's not just staying as hydrogen ions and hydroxide ions. In the next one, we have the molecular compound water form and the molecular compound carbon dioxide form. So that then is also a true double replacement reaction. We're not just mixing ions together. Letter D is not a true double replacement reaction because we have aqueous sodium nitrate, which again is going to exist of sodium ions and nitrate ions floating around in solution. Lithium chloride is aqueous, so that's going to be lithium ions and chloride ions. And if they're aqueous over here as well, that just means I've taken one mixture of ions and another mixture of ions and combined them together, but there's no new chemical substance formed. It's just all a bunch of ions floating around in solution. Combustion reactions, here we have a hydrocarbon, something made up of carbon and hydrogen. We combine it with oxygen and it's going to form carbon dioxide and water. These are always the products of combustion reactions, and we have to assume that this is going to be complete combustion. If there's not enough oxygen present, then you can't form all of the carbon dioxide in a sense. You will form carbon monoxide or black sooty carbon if there's not enough oxygen present, which of course can be extremely dangerous. Carbon monoxide being toxic, combining with your blood 300 times more readily than oxygen. So here's some examples of combustion reactions. If we combust methane, which is the major component of natural gas, with oxygen, it produces carbon dioxide and water. If we combust octane, which is the major component of gasoline, with oxygen, we get carbon dioxide and water. Again, we're always going to assume complete combustion, producing carbon dioxide and water. My last example here is not specifically a hydrocarbon because it also contains oxygen, but it is a combustion reaction and you are going to produce carbon dioxide and water, assuming again complete combustion. Identifying types of reactions, look for the generalized format. So potassium iodide is a compound. Chlorine is an element. Even if it's diatomic, it is an element. And so that indicates a single replacement reaction. And the chlorine is replacing the iodide in that reaction. In the second one, you have a single reactant forming more than one product. So that is going to be a decomposition reaction. And again, they require energy for the reaction to occur, being endothermic. Third one is forming water and carbon dioxide by something combining with oxygen. That indicates a combustion reaction. Second one, fourth one, you've got a single product. So you've got more than one reactant joining together. That is going to be a combination reaction. Next one, you've got a compound and an element. So that indicates a single replacement reaction. In this case, a more reactive metal, the sodium, is replacing the less reactive metal, lead. And the last one, you have a compound and another compound forming two different compounds. And so that is going to be a double replacement reaction. So looking at the generalized format, you should be able to predict types of reactions when given a chemical reaction. You should also be able to predict the products if given just the reactants. First thing you want to do is identify what type of reaction is occurring. So here's an element in magnesium. a compound in the lead 2 chloride. So that should tell you that is going to be a single replacement reaction, this case by a metal. And so then you've got to go to the activity series. If magnesium is more reactive than lead, which it is, it can replace the lead. And so that is going to form magnesium chloride and lead metal. The next reaction, we have two compounds. Sodium hydroxide is a compound. Calcium nitrate is a compound. So that's going to indicate a double replacement reaction. The calcium and the sodium are going to switch places. And so in the product side, instead of sodium hydroxide, you're going to get calcium hydroxide. And instead of calcium nitrate, you're going to get sodium nitrate. And calcium hydroxide is insoluble, so you're getting a precipitate, so that is a true double replacement reaction. Example 3, here's a compound reacting with an element, so it indicates a single replacement reaction. And so again, we need to go to the activity series. In this case, the periodic table. Is chlorine higher in the halogens than the bromine? The answer is yes. So the chlorine can replace the bromine. So they're going to switch places, giving you magnesium chloride and bromine. Next reaction, we have a hydrocarbon combining with oxygen. That'll indicate a combustion reaction. Products of combustion reactions, assuming again complete combustion, are always going to be water and carbon dioxide. So that allows the completion of that reaction. Next one, we have an element and another element. So it cannot be a replacement because there's nothing to replace. It is not a decomposition reaction because elements are the simplest substances in nature, cannot be broken down into simpler substances. It is not a combustion reaction that cannot produce carbon dioxide or water, so that is going to be a combination reaction, and the product is going to be sodium oxide. And those are the 5 types of reactions as we classify them in this chapter.